Hello guys, hope you're doing well. My name is Mahmoud and welcome to the new chapter of electrical circuit. As you all know, so far we were talking about a new component, or the diode, which is the combination of the P and N junction, and we somehow talk about the chemical wise part and somehow touch the electrical thing. But right now at this stage we would like to talk about it in detail and what would happen if we do have it in the circuit itself, what kind of formulas that we have to consider in order to solve a specific voltage or current related to that, because as we all know, we are dealing with nonlinear component and it's not as easy as the linear part, believe me. So without further ado, let's talk about it. So as you guys just remember, the last topic we were talking about the diode. The diode is going to be very important part of electronics, and this guy is going to be a heart of our work itself. So we do have it over here, and as you can see, the relationship between I and V, it's not just like the one that we do have in the resistors. It's a little bit non-linear. I have to say that it doesn't follow some kind of law that we used to know. So just before talking about the electronics and even talking about the diode or any other kind of specific component, let's just shift back. Let's just head back a little bit and talk about the actual component that we used to know, the resistors, right? In electrical circuit, our focus was on linear networks. It means that the relationship between V and I was linear all the time. It doesn't matter the time. It doesn't matter what kind of specific thing we have. Most of the time, we could find a relationship between them, solve some questions, and that's it. But we have to know that from now on, everything is not going to be as simple as before. So we have to deal with it. But dealing with the future factors needs us to somehow remember about the previous factors. That's why we do have a little bit of review. But just before talking about that, let me clear for you what does it actually mean when I say that we do have the barrier, that where superposition fails. As you guys just know, the superposition was one of the methods that we use in order to handle our circuit. It means that when I do have two resistors at a time, when I do have two sources at a time, for example, V1 and V2, and I'm looking for the current that goes inside the middle branch, for example, I call that I1, I could consider only V1, get rid of V2, find a current. At the next part, I can get rid of V1 and consider V2 and find another current. And the final step, the only thing I had to do was to add those currents that I found. It means that we do have the linear ability, or in general, we can say for linear circuits, the superposition must hold. It means that if X1 causes Y1, for instance, if the voltage 1 or the voltage for source 1 causes the first current or the first part of the current, and X2 causes Y2, at the end of the day, we can say that AX1 plus BX2 causes AY1 plus BY2. It's a general factor. But when we're talking about nonlinear devices, we don't have that anymore. It means that if I consider that my I out is the thing that I would like, if V1 is going to cause a current and V2 is going to cause another current, it doesn't necessarily mean that the output currents that I have because of V1 and V2 is going to be as the same as IV1 plus IV2. By the way, IV1 means that the current because of V1, I is sort of a function and V1 is the input itself. So at this point, I do have the semiconductor voltage current relationships is going to break this rule. And standard linear analysis tools cannot be applied directly. Remember that, guys, directly. Maybe we can find some way in order to apply it indirectly, but right now we cannot use it directly to the raw signal. So let's just have the small review about the linear parts. What we have, the very first thing we have was about the Kirchhoff's law. As you guys know, the accumulation of all of the currents that goes inside one node is as the same as all of the current that goes outside of the node. Or we can say that the accumulation of all of the currents by considering and respecting to their sign is going to be 0. So we have to know something about the KCL. The KVL, on the other hand, says that the accumulation of all of the voltages based on their sign in one mesh or loop is going to be 0. That's one thing. Then we had resistors. Obviously, you all remember that. If we do have the series resistor equivalent of all of them, what is going to be all of them adding up together? If we do have the parallel part, the equivalent would be 1 over R1 plus 1 over R2 plus 1 over R whatever we have. But you have to remember, at the end of the day, you have to find the reciprocal of that. So that was about the parallel section. We also had some kind of capacitors. Still, they're going to consider as a linear component. And we had some kind of the parallel part. It means that the C equal, if you do have the parallel condition, you guys remember it was vice versa of the condition that we had for resistance. For the parallel, we have to find a fraction in resistance, but in the capacitors was easy because we only have to add them up. On the other hand, in series, our work was a little bit challenging because we have to find the fraction of them. So that was not kind of the bad thing about this capacitor. Again, we had the voltage divider and current divider. You guys know better than me. And then we have the Thevenin and Norton. I told you that if we do have a linear some kind of system, we can replicate that with a voltage source and a resistance. Do we have to be in series, or we can use a current source and resistance in parallel. So we can do it for any kind of circuit that we want. And we did that in order to some kind of try to decrease the complexity as much as possible. We are going to touch that a little bit more exactly on the nonlinear section. So we had the V Thevenin is equals to I Norton times R Thevenin. You guys know all of the rules. And another thing we had was about the charging and discharging of the capacitors. It means that the voltage of capacitor is the final voltage plus the initial voltage subtracted by final voltage times e to the power negative t over tau. The tau or RC was the timing that it takes for my capacitor to get charged 63% of its maximum value. And you guys know the timing that it takes for the full charge, it was 5 tau. And we also had some rules about the discharging, which is not going to talk about it that much right now. Then obviously we had the parallel operator. It means that the R1, I just put it as an example, R1 in parallel with R2 is R2 divided by R1 plus R2. So at this point, the good thing was that the order doesn't matter, so we can use it all the time. And the grouping, it also doesn't matter, but we have to be careful that it's not going to be distributive. It means that if I do have R1 is in parallel with R2 plus R3, I cannot blindly say that R1 is parallel with R2 plus R1 parallel with R3. Oh, I cannot do that. We do have a couple of rules about that, but there are some kind of simple, but just in case, if we do have a case that R1 is way bigger than R2, then we can say that R1 in parallel with R2 is actually going to be the smaller one. And if we do have the N resistors side by side, the R equal is going to be R divided by N. So, before talking about the nonlinearity and any kind of formulas related to that, let's touch this point that in the real life, not all the signals are going to be either A or DC. At some points, we do have the combination of that. They're just AC bound, we know it. But the DC, when it's going to be combined with AC, is something we call as bias. The voltage bias, maybe you all heard about that, is the DC part of AC voltage. It means that that guy has the responsibility either to move some kind of sine wave, for example, the AC sine wave, up or bottom. Based on what? Based on the value that it has. The good thing about the DC bias is that we don't have to worry about it because that guy is not going to follow any rule based on the time. When you have a number for DC bias, that's the way it is. You just leave it as the way it is. You don't have to worry about each timing. That's a good thing. On the other hand, we do have a problem with AC. That guy is going to be a little bit complicated. As you guys remember, we had a formula for that. For instance, for a sine wave, V is equal to Vm, the maximum, times sine of omega t. You guys know omega is 2 pi f, plus the phi 0 or theta 0. It means that the phase angle at the very beginning. So we have to right now combine those things together. Not only we're going to stop there, we also have to put it in the nonlinear situation, because not all the time we are going to work with DC. We are going to be DC and AC. So again, as I just told you, we do have two parts for our signals. We do have the AC sections. We can show it as V with the index of D by the base on T, because as you know, this guy is going to follow some kind of the time, and it's going to be changed based on the time. Each variables could be changed. And another half DC component, we just call it as V. That guy don't change. So the VT, or the output voltage for the combination of AC and DC, is going to be DC voltage plus our AC voltage. So a static word we do have DC, and a changing world, we do have AC. So we are going to deal with those guys separately. And this one is going to enable us to use linear analysis tools like Fourier and superposition and the AC components that you're going to see in the future. So the one thing that we just saw was that the combination or the relationship between V and I was nonlinear. So it's just like not a line, just like a curve. And this is our job to somehow find some specific point. We do have one point that we call it as bias point. What is the bias point? The bias point actually, or we can call it as operating point, is the steady state condition. It means that DC voltage and current at this point, they are going to establish before any signal applied. It means that if we would like to work with our nonlinear component like the diode, we need a starting point. We have to find a point that is going to give us as a reference, because 0 is not a good point. So we have to find a 1 point, and we just consider it as a bias point. It means that at this time, I can apply DC input. This device settles at the Q point, which is called as VD and ID, and is going to be ready for any kind of AC signal injection. Because as you guys remember, right now I only have the VD based on ID, and this is the very specific thing, and it's completely related to the component that I have. But I still haven't talked about how much or what kind of voltage I am going to apply. So this point is going to help me to work on that. So let's talk about it. So at this point, some kind of assumption is that why not consider this specific point, which you have it over here, as a linear one. So we call it as the Taylor series. We are going to use that series by assuming the fact that base point, or that some kind of bias point, is considered as a linear system. For the nonlinear law, as you all know, the ID is going to be F of VD. What does that mean? It means that the current in your diode is going to follow a rule, a law, a nonlinear law of your voltage. What is the VD? VD is the voltage of your diode. What about input signal? We know that VD is actually, we consider two things. The VD, which is going to be a DC voltage, and small VDT, which is based on the time, and it's AC one. So at the end of the day, we can say that our Taylor expansion would say that F of VD plus VD, which we know it as the current itself, is somehow can be considered equal to F of VD plus F prime of VD times the small VD itself. What is happening over here? This is a little bit in detail mathematics. It means that the F prime is the derivative of F. What was the derivative? You guys know that the dF divided by dt is considered as derivative. Since we are talking about a very small point, it means that if I would like to consider the changes, rather than delta F over delta t, which we had it over some kind of linear word, at this point I have to consider it as df over dt. D and delta are somehow the same, but delta talks about the longer time span, but d is about the very short amount of time. So we can consider this part as our Taylor expansion, and right now we would like to talk about it in detail. So defining the small signal parameters is going to be our work. At this point, we are going to turn the calculus into components. At this specific point, we can have a very good assumption. Rather than just having our diode or any other kind of nonlinear component in itself, based on the mathematics, we can say that our small component based on the small signal injection can be considered as small signal conductance or small signal resistance. Why we are trying to do that? Because at the end of the day, in mathematics or any kind of science, we would like to try to simplify everything. By simplifying means that we would like to use some rules that actually we can play with. Because as you just saw, the rules of superposition or any other kind of law doesn't work for nonlinear case. So what would happen if I can convert it to something that those laws works? It means that I would convert my nonlinear section to linear section by considering the small and very some kind of little amount of changes. So right now I can consider as a conductance As you guys know, the conductance is a reciprocal of resistance. By using that, I can convert my nonlinear component to linear component. The linear component is obviously resistance. We can use that. So the GD, as you guys know, based on the some kind of conductance, is going to be the d by d over dVd at Vd itself. It means that at this specific point that I know it as Vd, I do have the relationship between the voltage and current, and that guy says that I do have the conductance. And as you guys know, the reciprocal of conductance would be resistance. Right now, I succeed to convert my linear condition or linear relationship, to linear relationship, and that's a good one. But remember, we can do it for small signals, and this complex nonlinear device can be some kind of replaced by a linear resistor only for the signal device or some kind of very, very small injections. So at the end of the day, we need the workflow. We need to know what are the steps that actually we can do that. So as we just talked about it, we can consider a couple of different steps in order to do that. The very first step is about the DC analysis. We have to find the bias points. As I just told you, VD and ID. By using what? By using only DC source. So on that point, as you just saw, VD, what was my DC voltage? So by using that, I'm going to find the bias points. Then I have to calculate the parameters. It means that I have to compute small signal derivatives, GD and RD, at the bias point based on the Taylor formula that we just saw. The third step would be about small signal equivalent. It means that right now I do have everything that I need. I do have a point, but I have to find, or I have to replace my nonlinear component with a linear component, which is a resistor. So draw the equivalent circuit, replace the device with RD, and we are going to short all of those DC voltage source. And the final one, we do have a linear analysis. It means that right now we can solve the voltage for gain or finding the impedance using the standard KVL and KCL. As you just saw, we reach from nonlinear condition to the linear condition, and actually we can use all of the laws that we already know. So let's see it in hypothetical condition. As you guys know, we do have the connection between a diode, which can be considered as a nonlinear, some kind of load or nonlinear component, with the connection of linear network. As I just mentioned, the linear network can be either shown as the V Thevenin and R Thevenin, or I and I Norton. So we are going to consider that. So we do have the diode itself. Actually, the voltage should be that way, not the current and voltage should be that way, not that way. Or we can say the voltage is going to be some kind of this way because this is positive and negative, but the current actually is going to be this way because all the time your voltage source should be bigger than the amount of voltage that's, as we all know, it's about the voltage that actually we need, or the potential that we need in order to help the P junction to move all of its electrons to the N junction. Cool. So right now, I would like to find a formula for my VD, the voltage of diode itself. So the voltage of diode is going to be F of ID. Obviously, at a specific point or at a specific time, the voltage of diode is going to follow its current, as we just saw. The V Thevenin subtracted by R Thevenin times ID. This is the normal, some kind of rule about the voltage drop. We can completely use it. So this equation is going to be what? Transcendental. We cannot solve it with simple algebra. We must use the numerical methods. That's why we need to resemble or replicate this guy with a resistance rather than by itself. So then we are going to do something fantastic. We are going to solve the unsolvable. We are going to use the numerical method. What does it say? It says that if I consider that this line is a nonlinear one, and I do have a formula for that. By the way, this is the formula for the diode. This is a very famous formula for that. It means that the ID going to the maximum current actually your diode can pass times e to the power of VD divided by NVT. The VD is the voltage of diode, and VT is just voltage of your terminal, and N is just a factor. It could be 2 subtracted by 1. So this is the formula that we do have for the current itself. On another hand, based on some kind of we know about the line, the ID can be written as the delta V divided by R Thevenin. It means that the V Thevenin by VT divided by R Thevenin is going to be my ID. What does that mean? It means that if I consider this guy as my reference, the voltage or the positive side of voltage is V Thevenin. This negative side of the voltage is VD, and by subtracting these two from together and divided by R Thevenin, I can find the current that goes through this point. Since right now I'm dealing with a series circuit, this current is going to be the same. That's why I can use it. By making these two guys equal to each other, I can reach to some points. So we are going to guess the ID and the component of VD, and we are going to use this formula. We do have the method, we call it as the Newton method. This Newton method says that find the zero of error, the function of GI, using derivative of update. It means that your I new is going to be I old subtracted by GI is going to be function divided by the derivative of I itself. By using that, we can solve the equation in order to reach to what factor? In order to reach to a case that some kind of replacing the diode with what? With the resistance itself. So whenever we're doing that, actually we are trying to have the small signal equivalent, and we have to consider a couple of things. The passive elements R, L, and C, at this point we only have resistor, maybe we do have a capacitor, maybe we do have the inductor, are going to be unchanged. The DC voltage source is going to be 0. The DC current source is going to be 0 as well. I know the voltage source means that the short circuit, if you talk about the 0, and the current source means that 0, it means that that guy is an open circuit, and nonlinear device can be replicated with RD. By having this guy or by having this system, we can somehow manage how to solve any nonlinear condition. I'm going to have so many questions for you. Don't worry about it. This was the rules that we have, but right now, the next chapter, we are going to talk about it. At some point, you would say that we deal with this, guys, and how actually we can see what is happening. At this point, you would say that we do have the software. The software, as you guys heard, there are different kind of software out there, but probably we are going to touch the one and only important software that we do have, LTS Spice. The graphical side is not that kind of beautiful. It's a little bit hazy, but still works. To be honest with you, I do have another software in my mind. It's some kind of the web application. That's Falstad. We used it in our previous courses, but right now probably we are going to use the LTS Spice because it's something that the industry works. And in that point, we are going to see that what would happen if we do have a nonlinear condition. What would some kind of numbers or my calculations are going to be as the practical or not. So at this point, we touch different parts. So at this point, we touched different parts and we talked about it. We talked about our beloved diode, and as we just can see over here, this was about the PN junction, but this PN junction is not going to be beautiful all the time. This PN junction is going to cause us some problem. What is that specific problem? That problem says that you cannot use the linear condition or linear laws that you used to know for the resistance and any kind of capacitors and inductor. At this point, you have to make your hand a little bit dirty and try to use other kind of ways. So we saw that how actually we can replicate or some kind of replace our nonlinear load with a linear one on a resistance by considering some kind of specific conditions. And in the next chapter, we are going to see that how actually we are going to use that in the real world. Again, if you have any question, please put down, comment me down below. I would be more than happy to answer that. My name is Mahmoud Kiasari. Have a great day, night, whatever. See you around.